Hello, am I audible? Okay, yeah. So, what we'll do today is we'll first solve last year's week six assignment. Then we'll solve this year's week six practice assignment. And then, as you said last time, you have some questions about the proof of the Baker-Gills-Soloway theorem. So, after solving these two assignments, we can discuss that theorem, the proof of that theorem. And if we still have some time, we can solve this year's week five assignment. Okay, so does that sound fine? Yeah. Okay. Okay, so let's start. Um, yeah. So the first problem is consider a randomized algorithm A for a language L which accepts X when X is in L with probability 1 plus 1 over 2 to the size of X. And when X is not in L, it accepts with probability 1 minus 1 over 2 to the size of X. So the question is, with respect to the algorithm A, what can we say about L? The options are PPP, PP, RP, and ZPP. So, which of these classes does L belong to? Could you like to guess? So, can it? Okay, so you are saying all of them. So, why can it belong to BPP?
So I think it could belong to BPP because there is a sufficient separation in the probabilities by which it accepts when it is in the language and when it is not in the language.
Okay, so what's the definition of BPP when X
Okay,
is in
sorry, it's not
language?
polynomial. It may not be in
Yeah,
BPP. Sorry, sorry.
right. Yeah, yeah. So this, yeah. So for BPP, this separation should be 1 over Pn for some poly n, right?
Yes, yes.
Yeah. So in fact, it's just in PP, and the reason is the following. So uh, if the success probability 1 over 2 plus 1 over f of n, then 2 boost the probability say 2 over 3. We need by repetition multiple times and accepting it runs. We need order fn repetitions. Yeah, so if so, yeah, since over here this is what 2 to the size of x, you need order to the size of x repetitions, which are exponentially many repetitions. And so this way of boosting the success probability won't work. And yeah, I mean, I won't prove this, but it's easy to prove that if you look at uh, the way we were boosting the success probability was using Chernoff bound. And if you look at that calculation, you will see that the number of repetitions is something like this. And so from whatever we are given in the question, we can't say that the language is in BPP. Similarly, we can't say that it is in RP and ZPP because both of them are contained in BPP. So that only leaves out PP. And the language isn't PP because in PP, what do we require? We require that if X is in the language, then it is accept, then the probability of acceptance is at least half. And if X is not in the language, then the probability of rejection is at least half. And that is satisfied in this question, right? So all we can say is that L is in BPP. Sorry, L is in PP. So is this fine? Yeah. Okay. So in that case, let's look at the next problem. So the next problem is any function f from 0, comma 1 to the n to 0, comma 1 can be computed by a depth 3 circuits using only AND, OR, and NOT gates. So is this statement true or false?
I don't think depth was mentioned in any of the lectures.
Okay. So okay. So the depth of a circuit. A circuit is a directed acyclic graph, right? With edges going from leaf towards the root, right?
Yes, yes.
So the depth of a circuit is equal to the length of the longest leaf to root path. So for example, suppose you have this circuit. Yeah, so what is the depth of this circuit? So these are the leaves, and okay, oh, sorry, these are the leaves. Yeah, and so the length is 1, 2, and 3. So depth of the circuit is 3. Okay, so is this fine? Yeah. Okay, so so now that you know what depth is, what do you think? Is this statement true or false? Okay, so the statement is true, and here's why. Yeah. So okay, so given f, write f in a CNF or DNF, or write as f as a CNF or DNF. First of all, do you know that every function can be written as either a CNF or a DNF?
Oh, what is a TNF? We know CNF, I think.
Okay, so CNF is a conjective normal form, so it is AND of odds. Similarly, DNF is a disjunctive normal form, so it's an OR of ANDs.
Okay.
Yeah. So, do you know that every F can be written in as both a CNF and a DNF? Okay. So then what all we need to do is, once we have written it like this, we can create a circuit. Okay, so let's suppose we have written it as a CNF, right? And what will that CNF look like? It would be an end of clauses, and every clause would be an OR of literals, and every literal is either a variable or its negation, right? So once we have written the formula in its CNF form, what we can do is the following. We can create a circuit whose first layer of gates uh, contain contains not gates. So I'm calling this the first layer. So the layer like closest to the input that I'm calling the first layer. It's not gates. Second layer can be depending on whether I'm writing it as a CNF or DNF. So if I'm writing it as a CNF, the second layer would be OR gates, AND gates. If I'm writing it as a DNF, and third layer would be AND gates if I'm writing it as a CNF, and there would be just one AND gate in the last layer. So let me just write it one AND gate. And if I'm writing it as a DNF, one OR gate. So however, the AND gates and the OR gates over here would have like unbounded fan-in, and that is allowed when you are talking about constant depth circuits. Otherwise, constant depth circuits are very weak because if you only allow fan-in 2, then constant depth circuits can only compute functions in constantly many variables. Okay, so uh, yeah, is it clear how you can write any function as a depth-free circuit, or do you want me to give an example and explain? Yeah, so if it
Actually,
is
what's the difference between CNF and DNF?
okay,
Like,
so CNF is okay. Let me write it over. So CNF is its full form is conjunctive normal form, and it is an or sorry, it's an and of clauses, and each clause is an or of literals. Okay, I don't have much space over here, so let me try to. So an example of a CNF would be something like this. Uh, x1 or x2 complement and x3 or x4 and DNF. So its full form is disjunctive normal form and it's an OR of literals. Sorry, OR of clauses. And each clause is an AND of literals. So for example, I can write x1 and x2, x1 complement and x2, or x3 complement and x4. Yeah. So is our CNF and DNF clear now?
yes, yes, very clear.
Yeah. And yeah, so yeah, and once you look at the definitions of CNF and DNF, it's easy to see that once you have a CNF and DNF, you can easily create depth-free circuits because, for example, over here, you need one layer of AND gate, NOT gates for these three. Then you need one layer of AND gates for these. And then at the very top, you just need one OR gate to compute all the ORs. Okay, so I hope this is fine. That's what the statement is true. Okay, so now let's look at the next problem. So in the next problem, we are given this circuit and we are supposed to find uh, the assignment set with this circuit. So we are supposed to say which of these statements is true, and in every statement we have some assignment and the output of the circuit. So Yeah, I won't ask you to guess which is true because this needs to be worked out. So yeah, let's just work out every option one by one. So the first option is uh, x1 is 0, x2 is 1, and x3 is 0. Just a second, let me connect my charger. I'm running on battery. Okay, yeah. So yeah, so when x1 is 0, the input to this NOT gate is 0. Okay, first of all, yeah, let me do it like this. So at the top in this circuit, we have an AND gate, right? So both of these should be 1. Only then the circuit would output 1. Even if one of these is 0, the circuit would output 0, right? So the output of both of these should be 1. Now, both of these are OR gates. So even if one of these is 1, we are fine, right? Okay, so what happens when x1 is 0? When x1 is 0, uh, this wire is 0. So this wire is 1 because it is a NOT gate over here. So in that case, we don't need to worry about what this wire is, right? Because since we have an OR gate and one input is 1, this is 1. So now we only need to check what this wire is. And for that, when x2 is 1, this wire is 1. And similarly, since x1 was 0, this wire is 1. That means this wire is 1, x3 is 0. Okay, so we don't even need x3. So over here, we have an OR gate, and one input of the OR gate is 1. So this is 1, and the output itself is 1, right? So when uh, x1 is 0, x2 is 1, and x3 is 0, we get the output is 1. So option A is true. Okay, what about option B? X1 is 0, x2, all three are 0. Okay, so what will happen in this? Since x1 is 0, this is 1, and so this is 1. This remains the same as before. X2 is 0, so this is 0. And since we have an AND gate over here, this is 0. Uh, x2 is 0, so this is 0. Again, we have AND gate, so this is 0. So this is 0 and the output is 0. Yeah, so B is also true. Okay, what about C? All three are 1. Okay, so can one of you tell me how? What should I do over here?
So x1 is 1 at the beginning.
Right.
Becomes, you can hear me?
Yeah, I can hear you.
So x1 is 1 at the beginning. So because
Right.
of negation, it becomes 0.
Yes.
And
So
x2
this is
is
1.
1 at the beginning. Yeah.
Right.
So that that is, I
Yes.
think we'll go with the x3 then, because there's an
Okay, yeah.
and gate there.
Yeah,
So
so,
x3 is
okay.
1
Yes.
at the beginning, and
Yeah, so
how do you
since
do
there is
that?
an OR gate
Uh,
over here, since there's an AND gate over here,
and
both
gate over
inputs
there.
are 1. This would be
The
1,
one,
right?
so one,
And over here, 0, 1 is 0.
0,
So this is 1.
0 and 1, 1. Uh, so 1
Yeah.
and 1, 1.
What was the option? Oh, the option says the output would be 0, which is 4. Yeah. Oh, sorry, this is what I didn't mark it. 101. Yeah, so similarly in this case, this is 1, this is 0, this is 0, this is 0, which means this is 0. Yeah, so in this case, this wire is 0 anyways. So we don't need to worry about this wire. And the output would be 0. And the option says the output should be 1, so this is also false. So only A and B are true. Yeah, yeah. The next problem is similar, but yeah, there are 5 variables now. And in so again in this problem we are given a circuit and we are supposed to mark all the options where the output is 0. So again, we need to work this out. So option A is x1 is 1 and everything else is 0. Okay, so to okay, so we are interested in output being 0. So and we have an OR gate at the top. So what should we be looking at? In particular, like what should we require for these two wires? Yeah, you are right. We require that both these wires should be 0. And yeah, so now let's look at this part of the circuit. So x1 is 1, x2 is 0, which means this is 1, x2 is 0, so this is 1, and so this is 1. So we already, just by looking at this part of the circuit, we already have that this wire is 1. And since we are an OR gate, the output cannot be 0. So option A is false. So now let's look at option B, x1 to x3 are 1 and the rest are 0. Okay, so again, x1 is 1. So this is 1 because there is no OR gate. This is 1, this is 1, this is 0. So this is 0 because we have an AND gate. Since this is 0, since this wire is 0, we also need to look at this wire. So x3 is 1. So we have an OR gate over here, so this is 1. X4 and X5 both are 0. So this is 0 and this is 0. So in option B, the output would be 0. So B is correct. Yeah. Now what about option C? Oh, wait, what was the option again? X1, okay, X2 and X5 are 1. Okay, so this is 0 and this is 0. So all of them is 0. This is 0, this is 1. Okay, in fact, I don't need to look at this either because there is AND gate. One input is 0, so the output is 0. X3 is 0. X4, oh wait, no, this is X4. Yeah, so in the option X2 and X5 are related. X2 is 1, X5 is 1. Okay, so X3 is 0, X4 is 0, so this is 0. Again, one input of an AND gate is 0, so the output is 0 and the output is again 0. So option C is also correct. And option D, everything except x4 is 0. Okay, so over here, yeah, this is 0, this is 0, this is 0, this is 0. This remains the same. X3 and X5 are 0. This is 1. Yeah. Yeah, so over here, like since X4 is 1 and we have OR gates, both are going to be 1, both are 1. So, and output would be 1, and so the output is 1. So again, this option is not true. So the only correct options are B and C. Is this fine, or do you want me to go over one some option again? Yeah. Okay, so then let's look at the next problem. Next problem is, which of the following randomized complexity classes corresponds to both-sided error? And the options are ZPP, BPP, PP, and RP. So which of these are true? Yeah, B and C, yes. Yeah, so in ZPP, there is no error. We keep on repeating the algorithm till we get the correct answer. And in RP, there is just one side. In particular, when an RP algorithm, uh, so when something is not in the language, the RP algorithm would always reject it, right? Yeah, so the error is just one-sided. So is this fine? Yeah. So then let's look at the next problem. The next problem is, we need to build a function and of x1 to xn, which is an AND of n input bits, and we are allowed to use only one OR gate of n in n and any number of NOT gates. So the question is, what is the number of NOT gates that is required? 1, n, n plus 1, and this is not possible. So which of these is correct? Okay, you are saying n. It's not exactly n, it's n plus 1. Yeah, because, okay, so are you aware of De Morgan's law? This one. So it says that the OR of n bits is the same as, and you need to take the complement of this whole thing again. Similarly, uh, x1 or I've written, yeah, so these are De Morgan's laws, and uh, what we are going to do is we are going to use this law. So we want to compute x1, the AND of x1 to xn. So here's one possible circuit using just one OR gate. So have a bunch of NOT gates, in particular have n many NOT gates in the first layer. Their outputs can be x1 to xn. Okay, let me first one. feed all of these to a common OR gate and then just feed this input to a NOT gate. And yeah, so what is this output going to be? The output is going to be x1 complement or xn complement, the whole complement, right? And this from the second De Morgan's law is just x1, the end of x1 to xn. So we have only used one OR gate over here and it had family n, right? So we are satisfying this condition. We are allowed to use only one OR gate of family n and any number of NOT gates. And the number of NOT gates we are using is 1. And there are n NOT gates over here. So that's n plus 1. Yeah, so option C is correct. Is this fine? Yeah. Okay, so then let's look at the next problem. Uh, which of the following classes is or are closed under complement? And the options are PPP, PP, RP, co-RP, and ZPP. So which of these are correct? Okay, so A, B, and C, you are, yeah, I think, yeah, you are right. BPP is closed, PP is closed, and ZPP is closed. Okay, so okay, so right now RP versus co-RP is an open problem. So if RP were closed under complement, then RP and co-RP would be the same, which would solve that open problem, right? But so far we don't know if RP and co-RP are the same, so we can't say that RP or co-RP are closed under complement. What about ZPP? So okay, so in PP, in BPP, PP, and ZPP, the acceptance and rejection conditions are symmetric, right? So when you okay, okay, wait, I can't say this for BPP, right? Okay, so for BPP and ZPP, the acceptance conditions are symmetric, right? So for example, X is in the language, you accepted it probably 2 over third, and if X is not in the language, you reject it with probably 2 over third for BPP, and for ZPP there is no error at all. You just keep on going till you get the right answer, right? So BP using the so this shows that BPP and ZPP are close near complement. It looks like this exact same argument should work for PP, but it does not work because because like there is no okay. So you are supposed to accept with probability at least half and reject with probability strictly less. So I'm sorry. So if X is in the language, you are supposed to accept with probability at least half and reject with probability less great. Sorry, and reject with probability. Okay, so if X is in the language, you are supposed to accept the probability at least half, and if X is not in the language, you are supposed to reject this probability. You are supposed to reject the probability at least half. And so when you flip this, what you get is when X is in the language, you are supposed to you are going to accept it with probability strictly less than half and the same thing. So what I'm trying to say is for PP, just like flipping does not work. So in fact, showing that PP was closed as a complement was an open problem for 14 years. But then I think someone showed that it is closed in complement. Yeah, so for the proofs for BPP and ZPP are straightforward, but the proof for PPP is complicated. Yeah, so let me just write why. So let me just prove that BPP and ZPP are closed in the complement, but I won't do the proof for PP. So for BPP, X in L, if and only if probability that MX equals to, oh, actually, let me write it like this. So probability MX equals to Lx uh, is equal is at least 2/3. So Have you seen some statement like this in class? Okay, why is my yeah, yeah. So okay, so what would this give me for L complement? So this implies that for L complement probability. Okay, so M prime X uh, simulates ellipse out. Okay, so why is this statement true? So suppose X were not in the language, then this is supposed to be true with probably at least two-thirds, right? And this means that when I flip M prime X is not equals to LX, this will be at least two-thirds. And since LX is equal, okay, LX and LX, so since this is true, when I flip it, mx equals to lx implies m prime x equals l prime x. So is this fine or should I write it down? Okay, so if this,
Can you write it down?
yeah, okay. Yeah, so, okay, so what does m prime do? M prime simulates mx and then flips the output, right? So mx is equal to lx is true if and only if m prime x is not equals to lx, right? Which means that m prime x, since both are 0, 1, m prime x and lx are 0, 1, m prime x not equals to lx implies m prime x equals to the complement of lx, right? Now, complement of lx is equal to L complement of x. Why? Because, okay, what does lx mean? When x is in the language, lx is 1. When x is not in the language, lx is 0. And so when x is in the language, lx complement is 0. But when x is in L, x is not in L complement, and so L complement x is 0. Similarly, when x is not in the language, Lx is 0. So Lx complement is 1. But when x is not in L, x is in L complement, and so L complement x is 1. So is this equality fine? Or, okay, like is this equality fine or should I can draw a table for this if it's not clear?
How is that both different? LX on top that bar
Okay,
and L bar X, how is it different? Like,
okay. So let me move this a little. No, and I can. Okay, so this is Lx. So, okay, like first, I'm just writing the definitions of Lx and Lx complement. So this function, so this is just supposed to be obtained by flipping this function, right? So this is, since this is the definition of Lx, this is the definition of L complement x, right? Similarly, what's the definition of L complement x? 1 when x is in L complement and 0 when x not in L complement, right? And so if I rewrite this 0 when x is in L and 1, wait. Yeah, so 0 when, yeah, so this x not in L becomes x in L and 1 when x is in L. Sorry, not in L. So yeah, both of them evaluate to the same thing, but their definitions are different, right? So is this fine?
Better.
I couldn't hear you. Can you repeat that, please? Yeah. So yeah, so this proves this statement, and therefore that BPP is closed under a complement. Yeah, were you saying something? Okay. So let me put the ZPP over here. So what is ZPP? So this is RP intersection co-RP. So suppose, okay, so, and I want to show that ZPP is closed under complement. So I want to show that if L is in ZPP, L complement is also in ZPP. So L is in ZPP implies uh, L is in RP and co-RP. So this implies that L is in co-RP as well as RP, which implies L complement is in the intersection of co-RP and RP, which is just ZP. Yeah, so this is why ZPP is closer to complement. So we have shown that A and C are true. Yeah, I'm not going to show you the proof of P because that's very long. So is this fine? Yes, then let's look at the next problem. So the next problem is, suppose we want to boost the probability of success of a co-RP algorithm. Which of the following is the desired approach? Run the algorithm multiple times, except if and only if at least one of the iterations leads to accept. Option B is run the algorithm multiple times, except if and only if all of the iterations lead to accept. Run the algorithm multiple times, except if and only if an odd number of iterations lead to accept. Run the algorithm multiple times, except if and only if a majority leads to accept, and there is no clear way to boost the probability of success. So, which of these is correct? Okay, you are saying that we should run the algorithms multiple times and accept if and only if at least one of the iterations leads to accept. Okay, so we are looking at a co-RP algorithm. Okay, and so what does it do when X is in the
It
language?
should be,
Can you repeat that?
it should be B, I think. Then
Yeah.
all of the operations should accept.
Yes. Okay, and why is that? Why is it B and not A?
Because when X does not belongs to language, in the language, then it may output like 1 or 0, like it may accept or not. So when the uh, when the algorithm outputs like yes, we are not sure whether X belongs to language or not. It is not a surety.
Right. So yeah, so we have a co-RP algorithm. When X is in the language, the co-RP algorithm always accepts. And when X is not in the language, the co-RP algorithm may sometimes accept, right? So a co-RP algorithm, Whenever a QRP algorithm rejects, it is always correct, right? So if we run the algorithm multiple times and it rejects even once, that immediately tells us that the string is not in the language, right? So we should reject if and only if at least one of the iterations leads to reject. That is the same as saying we should accept if and only if all the iterations lead to accept. Okay, so yeah, let me just write this. And that is just, yeah, so is this fine? Yeah. Okay, and so if the question were, uh, suppose we want to boost the probability of success of an RP algorithm, then which option would have been correct? Yeah, in that case, A would have been correct. Why? A similar argument. So an RP algorithm accepts implies X is in the language, right? So even if one of the iterations accepts, we must accept. And that's option A. Okay, so now let's look at the next problem. So the next problem is, suppose there is a randomized algorithm B which answers accept, reject, or do not know. And we have the following. When X is in the language, B always answers accept or do not know. And the probability of answering do not know is equal to 0.99. Similarly, when X is not in the language, then B always answers reject or do not know. Further, the probability of answering do not know is equal to 0.99. Then which of the following can we conclude from this and select all that apply? L is in RP, L is in co-RP, L is in BPP, L is in ZPP, or L is in P. So which of these are correct?
I think all of them should be correct except the last one.
Yeah, that is true. And notice that to prove that A, B, C, and D are correct, all we need to prove is that D is correct because ZPP is RP intersection co-RP. So if L is in ZPP, it's in both RP and co-RP. And BPP contains RP and co-RP. So if L is in ZPP, it's also going to be in BPP. And why is the L in ZPP?
So the algorithm is never wrong. Like it always accepts when it is in when X is in L, and it always rejects when X is not in L. Otherwise, it is a don't know.
Yeah, but over here, it's the probability is 0.99, right? While in the definition of ZPP, both of these are half.
Yeah, but
So
we
how
can
do you,
still boost it, right?
right? And why can we boost it? Because this is 0.99, which is 1 minus 0.01. Sorry, wait. This is half plus 0.49, right? So the gap over here is just polynomial, right?
Yes.
So we can boost it in fact, it's a constant gap. So we can boost it in like constant number of iterations. Yeah. Okay, so that was this last year's week 6 assignment and this year's week 6 practice assignment. So last time you said that you had some questions about the proof of the Baker-Gill solvability theorem. So if you want to ask those questions now, we can discuss them now and then move on to week 5 assignment?
Yes, give me just a moment. I'll
Yeah.
ask the questions. So I had the doubt in the second part of the proof, like
Okay.
where like we try to build a language such that p with oracle b is not equals to np with oracle b,
Right.
right? So like since we are building a language in a
Hello, your voice
language of our
broke.
am I
So I
audible
couldn't.
now?
Yeah, you are audible now.
Okay, so what I meant to ask, like the language itself is being constructed in the proof itself, right?
Yes.
So how is like I couldn't get around the idea that how is such a language being used to prove uh, the inequality we started with? Like, could you give an overview or something?
Okay, so our goal is this, right? So this is our goal, and it suffices to show that. So yeah, this is okay. If we prove this, we would be done, right? So even before defining A, what we are doing is this: we are defining L to be UA. Okay, so what the proof does is the following: for any language A, it defines a language UA as follows. Okay, 1 to the n, where some string of length n is in A, and we are going to show that there exists an A such that UA is not in P to the A, but is in NP to the A. So first of all, is it clear that if we show the existence of such an A, then we are done?
Yes, yes.
Okay. So now, how are we constructing A? So do you remember the construction of A?
Yes, yes, I remember. Like we started constructing it iteratively. So, like if we go through your, because I have doubt in many of these steps. Like,
Okay.
so how do we discuss that?
Okay. So one thing I can do is I can write. I won't
Uh,
write the proof in all the details, but I can
uh,
write some of
you may
the.
just like open the lecture notes and we can go through there also.
Okay. Yeah. So I'll have to log in. Oh wait. If I open in my computer, you won't be able to see it, right? So it's better if you open as well.
I have it open.
Okay, okay, then it's great. Yeah. This was in week five's content, right?
Week five's content.
Yeah, yeah, you are the notes. Was it lecture 25, 26, or
Uh,
27, 29?
and it's 26.
Okay, yeah.
Page 3 of PDF.
Okay, yeah, let me open the PDF. Yeah. Okay. Speaker with sound. Speak time to load. Let me try down. Okay. Let me do one thing. Let me stop my video for a while, download it, and then take it from the video again. Okay. Now I can open the entire. Yeah. So okay, I'm on page 3. Yeah. So you can ask me a question now.
Okay, so like we start like here it says that we'll construct B such that UP belongs not to P with oracle B, and MI is simply the like representing each stage of the polytime oracle Turing machine we are like having, right?
Yes.
So afterwards it says that at ith stage MIB does not decide UB. So there is a particular Turing machine with oracle access to the language which does not
Yes.
recognize that language, that particular one. But what I mean to say, there may exist another Turing machine which would recognize this language.
Okay. So what does the statement say? We will construct B in stages such that after the ith stage, MIB does not recognize UB. Okay. So now take any Turing machine.
Okay,
Since Turing machines are countable, there would exist a J such that that Turing machine equals MJB, right?
right.
So what does that mean? That means that in the jth stage, whenever we reach the jth stage, MJB does not decide UP, right?
Okay.
So basically, this is diagonalization. In the ith
UB,
stage, we are
so
just
like
make, yeah,
MJB would not decide UB, which would be like UB is evolving itself, right,
right.
through the stages. So at the whatever UB would be at the jth stage, MJB would not decide that.
No, 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 no.
Okay.
Okay, so even though UB evolves,
Mhm.
we would ensure throughout the proof that it evolves in such a way that, let's say in the ith stage, MIB did not recognize UB at that point in time, right?
Okay.
Then we would evolve UB in such a way so that if it did not recognize UB at the in the ith stage, it would also not recognize the modified UB ever. Okay,
Okay.
that is what happens in the proof. And so yeah, so when we go to the proof, I'll point that out why that is true. Okay,
Okay. So
yeah. So sort of this is backwards compatible.
okay, so any
Yeah,
like Turing machine for like greater than I would recognize the whatever stage UB was in like before it. Right.
okay. It may or may not recognize that.
Okay.
So all we are saying is in the ith state, we would ensure that MIB does not recognize UB.
Okay.
So initially, what we would show is that MIB does not recognize UB at that point in time, but UB would evolve in such a way that it won't recognize UB even after the modifications have been made. We are not saying that MIB recognizes UB as it was in the I-1 iteration. We are not commenting on that at all. Okay.
Okay. So,
Yeah.
like, when would we obtain a language A or B, whatever we say, which would like give us the inequality? Like, because we are talking about stages, like for a particular stage,
Right.
there exists a language, for another particular stage, there exists a language, and corresponding to Turing machine with Oracle access.
Right.
Like, the language itself is like in stages. It never like completes itself or
Right. So there is this
like
infinite process, right?
right,
That infinite process itself constructs a language.
right.
So, for example, if you're only interested in knowing that, okay, so I have a language, I want to consider a language B, right? One way of thinking about a language B is it's thinking of B as a union of B0, B1, B2, B3, and so on, where Bi, or I should use J, where Bj is the set of all strings of length J in B, right?
Okay, set of all strings of length.
J in B.
Okay,
Okay, so one way of thinking of B is this, right? And what will happen is, if you look at the proof, and again, I can point this out, after some stage, we would have figured out Bj completely. So for every J, there exists a stage I. So that after ith stage, Bj would have been completely figured out.
okay. So
And
like what
since,
does it mean by completely figured out here?
okay, by completely figured out, I mean that we would have decided which strings of length J are in B and which strings of length
Okay,
J are not in B.
okay.
Yeah,
So can we just go over the like, okay, till now it's clear, and the description of a particular stage.
okay,
Could you just walk me through it? So,
yeah. So that's on page 5, right?
right, yes.
Okay, so the stage I says, okay, maybe you can read and then tell me where you have
Okay,
issues.
the just this statement. After 2 raised to the power n by 10 steps,
Okay,
MIB
okay, okay.
says
In
like
that case,
what?
let me read the first three statements so I know what's going on.
Okay,
Okay, run mi to the b on 1 to the n for 2 n over 10 steps. Okay,
okay. So this is exponential, right?
right.
So how is a deterministic Turing machine able to run
Okay,
in exponential steps?
okay. So right now, what we are doing is we are constructing this language in this infinite process, right?
Okay,
And in that process, we are running mi to the b on 1 to the n for 2 n over 10 steps. So first,
right.
this process does not have to be point in time, right?
Yes, yes. Okay.
And
Why?
what this, yeah, okay, so this is an infinite process where we are just
Right.
creating a language, right?
Yes.
So there is right now we are not talking about the computational complexity of the language at all, right?
Okay, okay. So it is the creation process. It doesn't like go
Right.
with the computational complexity.
Yeah.
Okay.
And what we are saying is in the creation process, we would run mi to the b on 1 to the n for 2 to the n over 10 steps, right? What this statement means is that we would run mi to the b on 1 to the n for at most 2 to the n over 10 steps.
Yes, yes.
And this is possible, right?
Yes, yes. Right.
Yeah.
Okay, so just a minute. So like uh, we are intentionally constructing a language such that we are leaving some of the strings outside by doing 2 raised to the power n by 10. So we are only going over a part of the string of length n, and this ensures that some of the strings of that length n is undecided for the moment, whose status
Okay.
we do not know. And our intention is to flip the output for whatever we know any in each stage.
Yes.
And as a result, what we get is finally the Turing machine with Oracle at a particular stage is failing to recognize the language at that particular stage. Am I right?
Okay. Right. So I think if you are clear till what point?
No, I think that's all.
Oh, so no, there is one more thing, right?
Okay.
You said that MI does not recognize UB at that stage, right? But you initially at the very beginning you asked me, how can we be sure that MI does not recognize UB after the end of the entire process, right? That we still need to clear, right? Get cleared, right?
Yeah, I was confused about like this says that MI does not recognize UB. Okay.
Right. Right.
at a particular stage. But what I was confused about that there may exist some other Turing machine which would recognize this.
Okay. Yeah. So that would be MJ, and that would be taken care of in the jth stage.
So you are saying that such a Turing machine would exist in future of this iterative process.
Right.
Okay. So okay, like can we have some intuition for that? Like, or I may take your word for it.
Okay. So uh, first of all, we are only looking at Turing machines which run in polytime, right?
Yes, yes.
So the set of all Turing machines is countable, right?
Okay.
So I can number the Turing machines as M1, M2, M3, and so on.
Okay.
Since the set of all Turing machines is countable, the set of all polytime Turing machines is also countable because it's a subset of the
Okay.
previous set, right?
Right.
So I can label all the polytime Turing machines as M1, M2, M3, and so on, right?
Okay.
Now, what do we want to do? We want to say that for every polytime Turing machine, it fails, right? It
Yeah.
cannot recognize UB.
Okay. Yes, yes.
So, since it's a polytime Turing machine, there exists a J that MJ is that machine, right?
Okay. Yes.
Why? Because we have numbered all the polytime Turing
Yes,
machines.
yes.
So, and MJ would be taken care of in the jth stage.
Okay. Right, right. Okay, so
Yeah,
it's clear now, I think.
yeah. And I think there was one more doubt, right? That all in the ith stage, all they are ensuring is that MI does not recognize UB as it is right now, right? But we are going to modify UB in the future. So how can we guarantee that it won't recognize the final UB, right?
Yes, like, but I think wouldn't it be taken care of like from the induction hypothesis, something like that, because we're ensuring it in each stage and the following stage
Yeah,
takes care of that.
right. It would be taken care of by the induction hypothesis, but okay, so okay, in the proof there is some statement, right? That MI does not. Oh, wait. Okay, so the last statement, as a result of on page 6, as a result of the above, MIB always gives the wrong answer on 1 to the n, right?
Yes, yes.
And why is this true? Because in the subsequent iterations, we are not going to add, we are not going to touch bn at all, right? We are not going to either add or subtract a string of length n from b because we would only worry about strings of length more than n, right?
Yes, yes.
So this is why in the ith for every I, there is an n such that in the ith stage, so after the ith stage, bn does not change at all. And what the proof does is it ensures that uh, like the Turing machine MI makes mistake on 1 to the n. And since Bn does not change after the ith iteration, if it made mistake on 1 to the n in the ith iteration, it cannot rectify this mistake after some other iteration, right?
Okay, yes, yes.
So for example, if okay, can you go back to the previous page?
Yes,
Look at
yes.
the second line. Choose n greater than n. If this statement were not there in the proof, then we would not have been able to argue that the Turing machine, MI, fails or to recognize UB. Because it is possible that it says that 1 to the n is in the language. In the ith iteration, we ensure that there is no string of length n in the language. But in some subsequent iteration, we added some string of length n in the language, right?
Yes, yes.
But this is not possible because in the subsequent iterations, L would be always greater than N. Sorry, N would be always greater than L.
We are always increasing the length of the string. So smaller
Exactly.
length strings are always like there as it is. They are not changing.
Right. Yes.
And we are failing for those at every stage in future.
Yes. Right.
Okay, okay. So I got that. Thank you.
Yeah.
Just one more thing. In
Yeah.
week 5, I think there was a question regarding which of the theorems could be proved using diagonalization. Right?
Oh, yeah. So we are coming to week 5 assignment now.
Okay, okay.
Yeah. So, okay. If there are no more questions about Baker-Hill's theorem or any other thing, then we'll start week 5.
Yeah, yeah, you may start week
Yeah.
5.
Okay. Yeah. So the first problem from this year's week 5 assignment is consider a randomized algorithm A for deciding a language L in polynomial time. If X is in L, then A accepts X with probability 1, and if X is not in the language, then A accepts X with probability 0.2. Using this information, what can we say about L? It's in RP, it's in co-RP, it's in BPP, and it's in ZPP. So which of these are correct? Okay, it's in co-RP and it's in BPP. Yeah, that is true. So why is it in co-RP?
Because it accepts always when the x belongs to L.
Right. Yeah, so it accepts always when X is in L, and when X is not in L, it accepts with probably 0.2, but 0.2 is like less than half, right? So we don't need to boost, don't need to do anything. We can directly say that language L is in co-RP. Okay. And since it's in co-RP and co-RP is contained in BPP, it's also in BPP. So is this fine? Yeah. Then let's look at the next problem. Consider a randomized algorithm R for deciding L. If X is in L, then R accepts with probability 0.8, and if X is not in L, R accepts with probability 0. Consider a new algorithm prime for deciding L. R prime runs R two times on the input with independent random coins and rejects only if both the runs reject, else accepts. So what's the error probability of R prime? So we did something like this in the last time as well. So, okay, you are saying it's 0.04. Let me check. Yeah, it would be 0.04. Yeah, yeah. So, yeah, probability that uh, R prime. So, probability that R prime. Okay, so first let me do that. The R prime accepts when L. So, this is the same as 1 minus probability that R prime rejects, right? Okay, let me do it. Yeah, the prime accepts X. So we need to look at both cases. R prime X is in L and X is not in L. So when X is in L, it's this, which is equals to 1 minus first run rejects and second run rejects X. Okay, so now what should I write next?
You can multiply the probabilities at both these stages.
Oh, so are you saying that I should write probability first run rejects X times probability second run rejects X?
Yes, because they are independent, I think.
Okay, that there is one problem with that. It's okay. So what I
Yeah,
can write
one.
is this. Because, okay, so why do I need this conditional probability over here? Because, so we are running this algorithm in sequence, right? So you would run the first iteration, then the second iteration. So if the first iteration had accepted, then this won't make any sense at all, right? Because we won't even run the second iteration. So saying that the second run rejects only makes sense when the first one is already rejected, right?
Yes, yes.
Yeah. So now we can do this. So now we can see that this probability is 0 0.2 and this is 0 0.2. So this is 0 0.2 is clear. And for this is 0 0.2, we are using the fact that we are using independent random bits. So this is 1 minus 0. So yeah, is it clear why we need this conditioning? Yeah, okay. That said, some people and even some books would just write probability second run rejects X. But even when they write that, what they mean is this, right? Because second run rejecting makes no sense if we don't even run the algorithm for a second time, right? So sometimes you would find just this, but what they mean is just this. Yeah. And because another way to write this is second run rejects X and second run was indeed carried out, right? Yeah. Okay, so, oh, yeah, okay, so this is the probability that R prime accepts X. And now we need to look at, yeah, the second trivial case. X is not in L. In this case, probability R prime accepts. This is 0. So in this case, there is no error. In this case, there is error, but yeah, it's just 0.04. So is this fine? Yeah. So then let's look at the next problem. So the next problem is if Rp equals P, then which of the following statements is or are true? Mark all the correct choices. P not equals NP, Rp equals co-Rp, P equals ZPP, and P equals BPP. So which of these are correct? You are saying the B and C are correct. B is, yeah. Okay, so why is B correct? So can you tell me why is B correct?
Yes, because P is contained in RP and P is also contained in co-RP, and P is closed under complementation.
Okay, yeah. So what we have is this. P is contained in co-Rp and okay, let me write it like this. So P equals to Rp and P is equal to OP. That is P is closed in complement implies that P contains co-Rp. Co-Rp contains P, so P equals co-Rp. Yeah, and Rp equals P, so Rp equals P equals co-Rp. So B is true and ZPP is just, yeah. So both B and C are true. So now let's look at the next problem. I think you were mentioning this, right?
Yes, yes.
Proofs of which of the following theorems use diagonalization? Time hierarchy theorem, space hierarchy theorem, vaulting problem is undecidable, and Lardner's theorem. So what was your question about this problem?
Uh, like I say that all four should be correct.
Okay, so you are not wrong. So there is a proof of Lardner's theorem using diagonalization. In fact, the original proof given by Lardner was using diagonalization.
Okay,
Yeah, but
you
I
also
think
marked
this
in.
in this question, what is meant is like from the proofs we saw in class. Which of these is diagonalization?
Okay, so but it was mentioned in class, so I didn't know.
Oh, okay. So, okay, I think what you're saying is he mentioned in class that Ladners can be proved as a diagonalization.
No, the proof for Ladner's uses diagonalization, but we will see an overview or a brief like how the proof works. So
Okay.
the overview was discussed, but it was said that proof uses diagonalization.
Okay. So, which proof did he discuss?
For,
Was it
for
that you
Ladner's
construct a
theorem,
function HN?
like in that we use padding, I think.
Okay.
Yes,
Okay.
padding was discussed.
Okay. I don't think that the padding proof is his diagonalization. Yeah. So, I don't think the padding proof is his diagonalization, but Ladner's theorem can be proved as a diagonalization as well. So, if you have a doubt, you can like put this in the forum. The instructor might like update the options which are correct.
Okay, okay, all right.
Yeah.
So
Yeah,
does
but
the padding proof use diagonalization? Like, are we sure? But I do
I
not know whether it
don't
uses or
think
not.
it does because the way it works is so you
There one thing
add.
was left in that proof. Like we need to figure out how much padding we need to do such that it isn't in P, but it comes out. Like what I mean to say that the problem is no longer in P, but it is also not in NP.
Okay, so okay, so was this mentioned the padding is 1 to the n to the HN, where HN is some function. Was this mentioned?
One to the H. No, no.
Okay,
As much as I remember, like for a three set problem, we padded with something such that the string length of the resulting string with padding is exponential. Like for example, this SAT
right.
problem was of length n, so the string is now somewhere around order 2 raised to the power n after padding.
Okay,
And if we now solve it, so if like even we solve the satisfiability problem in 2 raised to the power n, it will be still be linear in terms of the entire string length.
okay, right, yes. If that is what we do. So okay, the padding is in fact this. Padding is 1 to the. Sorry. Yeah, so the padding is of exponential length. And I think what was left out in class was the construction of this edge, right?
Yes, yes, like the amount of padding we need to do.
Yeah. Okay, so the construction of edge, what is it? Have to just go to log n. So I don't see how it uses diagonalization. Yeah, so I don't see how the construction of edge uses diagonalization over here.
Okay, so like using the argument that the original proof for Lardner's theorem uses diagonalization,
Yes.
should the option be correct or what? Like
Yeah,
because
so
nothing is
it
mentioned here.
depends on what the instructor had in mind when they asked the question, right? So I mean, there is a proof using diagonalization. But by proofs, what did he mean? The proof, any proof or proofs that were covered in class. So I think you can like ask for a clarification of this in the forum. I think that
Okay,
would be the best.
all right.
Yeah. Okay. Yeah. So if this is fine, we can look at the next problem. So the next problem is which of the following theorem says that P versus NP problem cannot be solved using diagonalization, time hierarchy theorem, Savage's theorem, Lardner's theorem, or Baker-Gibbs-Holloway theorem. So which of these is correct? Yeah, you are right. It's Baker-Gibbs-Holloway theorem. Okay, so next problem is suppose we want to boost the probability of success of an RP algorithm. Which of the following is the desired approach? Run the algorithm multiple times and accept if and only if one of the runs accepts. Run the algorithm multiple times and accept if all runs accept. Run the algorithm multiple times and accept if more than half the runs accept. And ec- run the algorithm multiple times and accept if at least two-thirds of the runs accept. So we already did this, right? By looking at a similar question for QRP. So the answer is A, right? Yeah, any one of the runs accepts. So is this fine? Yeah. Okay, so let's look at the next problem. The next problem is polynomial identity testing is known to be in which of the following classes? P, NP, PPP, or ZP? So which of these are correct? Hmm. So you are saying it's in BPP. Okay, that is true. Yeah. So why is it in BPP?
I don't remember it clearly, but it is in either of P or RP or co-RP. It is in one
It's
of
in
them.
QRP.
Okay,
Okay,
yes.
so
So
okay,
that's why it is in BPP.
yeah. So if it were in RP, then NP would also be true, right?
Yes, yes. Okay.
Yeah. Okay, so yeah. Why is it in RP? Sorry, why is it in QRP?
I think the problem is to check that whether for all input, uh, whether for all values of x, the given equation is always zero.
A given polynomial equation is always zero, right?
Given polynomial equation. So
Yeah. So
like since
the
it is a for
language is
all, we
this.
can directly say that it is a co-RP.
Oh no 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 no. Okay,
Uh, like
that is not the
complement
problem.
languages.
The problem is this: all polynomials which are identically zero. Okay.
Sorry.
So the problem is this: a PIT is the set of all polynomials in n variables which are identically zero. That is, when you write the polynomial as a sum of monomials, the coefficient of every monomial is zero, right?
Yes.
And that is equivalent to saying that okay, the polynomial evaluates to zero at every element, like regardless of what you put in place of x1 to xn. So what I'm
Right.
saying is, yeah, but from here you can't directly conclude that it's in co-RP, right? Because like, what do you have for co-RP? So what's the definition of co-RP?
No, no, I meant like, yes, obviously we can say that even if we find a one assignment which leads to the value being non-zero, we can say that it is not the part of the language. But
Okay,
if we keep finding all the values are zero for all the runs, so still it may be in the language with some probability.
right.
And like, so since we are never wrong on the no instances, it isn't co-RP, and we are right with like we may get sometimes false positives, so it is like these are the conditions for co-RP.
Yeah, but there is also this probability bound, right? That our error probably shouldn't be too large.
Yes, like it should be less than half.
Yeah. So and why is that true?
I think like the answer would be boosting, but I'm like
Okay, so suppose that uh, there exists only one. Okay, so suppose that P is non-zero. Okay, but there exists only one point A1 to AN, so that P of A1 to AN is non-zero. For every other point B1 to BN, P of B1 to BN is zero. Okay, then what would be the success probability of your algorithm?
like 1 over 2 raised to the power n.
Oh no 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 no. Okay, so over here, what is the domain of x1 to xn?
Sorry, domain of x1 to xn, like it is the entire like the set of real numbers.
Right. So you can't say it's 1 over 2 to the n, right? Because if there were just one point in the entire R to the n at which the polynomial was non-zero, then the probability of you picking that point is zero, right?
Yes, yes.
So we somehow need to bound the, so we somehow need to say that, okay, there are a lot of points at which the polynomial would be non-zero, right?
I didn't get that.
Okay, so as I said, if there was just one point at which the polynomial were non-zero, then the probability of the success probability of the algorithm that you suggested, just pick a random point, evaluate the polynomial at that point, and check if it's zero or not. That would be zero. In order to show that the success probability of this algorithm is large, what we need to roughly argue is that there are a lot of points at which the polynomial is non-zero, right?
Yes, right.
So how is that true?
Okay.
Okay, so yeah, okay, yeah, think about it. You can think about it till that I will write till then I will write down this algorithm that you suggested. At the degree of PB at most be big S to be any such size 2D uh, where they are uniformly at random from S for all I in N. Uh, evaluate P at A1 to AN if it is 0 except otherwise reject. So this is clearly a polytime algorithm, right? Also, when P is 0, P of A1 to AN is 0, and the algo accepts. So when P is 0, there is no error. What about the other thing? Sorry, sorry. When P itself is, so this is the claim I want, right?
Yes, yes.
Yeah, so this is what we want to prove. And so how is this proved? Was this covered in class?
Like I do not remember, but I
Okay,
think
so
we didn't
was the
go into.
Schwarz-Zippel lemma covered in class?
Sorry?
Was the Schwarz-Zippel lemma covered in class?
No, I don't know. Like I didn't think there was any such name mentioned.
Okay, de Miller-Lipton Schwarz-Zippel.
No, I've heard that first time.
Okay, so yeah, the lemma goes by two names. Okay, so
I think
let me
I
write.
got the answer for your question like earlier.
Okay, yeah. So
Like you
what's
said,
the
like how would we say that there if the polynomial equation is non-zero, so
hmm,
there would be like the probability to find that the probability the equation is non-zero, it'd be high,
hmm,
would be non-zero. So what I mean to say is that since you wrote that degree, since
okay,
the degree is would be something, some finite thing, some finite number. So if it is non-zero at some point, so number of values for it which it would be zero would be at most d.
That is only true when the polynomial is just one variable. For example, consider this polynomial. Uh,
Okay, so I thought like it was infinite. I
X
don't know
square
for
minus y
multiple
square.
variables.
So what is the degree? Okay, so there are n variables, like x1 to xn.
Okay, so
Yeah, so consider x square minus y square. The degree is 2, right? How many zeros does this have?
I think all the points on the circle.
No, no, no,
So
no.
it,
All the points of the line x equals y.
okay, yes, all the points on
And
the
x
line
equals minus y. Yeah, so
x
this
equals
is,
max.
yeah, so
So
x
that would be
minus
infinite.
y, yeah, x plus y is this. So like both those lines are in zeros, right? So there are infinitely many zeros.
This is
Okay, so what? Okay, but yeah, you are right. So if the polynomial were univariate, then there would just be d zeros. You, there is a somewhat similar statement for multivariate polynomials as well. It's called the Schwarz-Zippel lemma. Yeah, and what this says is the following. Yeah, so what I mean is that P is non-zero of degree D, and S is a subset of R of size 2D, right? Then, then probability over A1 to AN picked uniformly at random from S, E of, yeah. So this is the statement. So now, using this statement, can you argue that that this is true?
well, you have constructed S such that its size is 2D, so that would be half.
Yeah. So this would be at most half, and so
So for
like
not equals to 0,
yeah,
it would be greater than equals to half.
correct. Yeah. So yeah, but okay, this is basically the extension of that univariate thing that you mentioned for multivariate polynomials. Yeah, so is this fine? Yeah. Okay, so if this is fine, then let's look at the next problem. So which of the following statements are known to be true? Mark all the correct choices. BPP is in NP, RP is in BPP, RP is in NP, and ZPP equals RP intersection QRP. So which of these are true? We have seen things like this multiple times. Yes. B are true. Yeah. And what about BPP, subset of NP? Like, do we even know that? So yeah. Yeah, so we know that P is contained in NP, RP is contained in NP, but we don't even know that BPP is contained in NP. So it is possible that there are some problems which you can't solve in NP but can solve in BPP. Yeah. Even though we don't believe that is true, but as of now, we can't rule out this possibility. Okay. So then let's look at the next problem. The next problem is suppose y is a random variable that takes values in the interval -1 to -100 to 100. If the expected value of y is 5, then as per Markov's inequality, what is the upper bound on probability y greater than equals to 30? 1 over 5, 1 over. We cannot infer anything given the and any of the given choices using Markov's inequality. So which of these is true? Okay, you're saying D is true. Why is that?
The interval should be non-negative for the random variable.
Yeah, so Markov only applies for non-negative random variables. So here it can take values from -100 to 100. So it's not non-negative. So you cannot apply Markovs. So is this fine? Rather, I should like it like this. Okay, so suppose that, just let me modify the question and say that suppose that uh, y is in this interval. Then what's this? Yeah, then what's an upper bound on this? In that case, using Markovs? Yeah, it's 1 over 6 because probability that, oh, sorry, greater than equal to 30. Expected is upper bounded by the expected value of y over 30, which is 5 over 30, which is 1 over 6. Yeah. Okay, so let's look at the next problem. So last Vegas algorithms correspond to which of the following complexity classes? RP, ORP, ZPP, or NP. So which of these are correct? ZPP is correct. And assuming P equals BPP, which of the following statements are true? P equals NP, P equals RP, P equals co-RP, and P equals ZPP. So which of these? Yeah, B, C, D. Yeah. Okay, so Y is P true? So P is contained in RP. I can prove it. P is contained in ZPP, RP, and co-RP, all of which are in turn contained in BPP, which is equal to P, right? So since there is an there is a P over here, there is a P over here, all these two must be yeah. So let's look at the last problem. Consider the following randomized algorithm for deciding if a given undirected graph has a k-clique. For each vertex in the graph, we decide to select it or discard it with probability p greater than 0. The algorithm then checks if the selected vertices form a k-clique. If yes, then we accept. If no, we reject. Choose all the correct statements out of the given options. The algorithm is always correct. The algorithm runs in polynomial time. The algorithm may give false negatives but never false positives. The algorithm may give false positives but never false negatives. And so which of these are correct? Yeah, you're saying B and C are correct. Yes, why does the algorithm always run in polynomial time? Because we are picking things randomly at one time and checking if if it's a valid click or not. Picking vertices randomly takes poly time. We just have to go over it once, go over the list of vertices once, and checking out if they form a K clique also takes polynomial time because it's just a verification step. And for NP problems, verification is poly time. So B is true. What about C? The algorithm may give false negatives, but never false positives. So suppose that the graph had a K clique, then it is possible, in fact, with very large probability, we won't pick that. The algorithm may say that a graph that does have a K clique, the algorithm might end up rejecting that graph. So false negatives are possible. And what about false positives? If the graph does not have any K clique, then no matter which set of vertices we pick, it's not going to be a K clique, right? The algorithm is not going to accept it. And so there are never going to be false positives. Yeah. So is this fine? Yeah. Yeah. So that's it. So yeah. So if there are no other questions, we can end the meeting today a little early.
Just one minor thing, if you
Yeah.
could go over it. Uh, it was given like in the starting of the proof for Bickergill. Most diagonalization proofs relativize. What does relativize mean?
Okay. So relativization means the following: that if something, okay, so we say that a proof relativizes if suppose you prove that you prove something for A and B, where A and B are some complexity classes, okay.
Okay.
Then we say that a proof relativizes if it also holds true for A to the O and B to the O for any oracle O.
Okay. But yes, this was also given here. But any oracle O means like we are not keeping in context the power of the oracle O itself with respect to the classes.
Yeah.
So
Yeah, so that's what happens. So okay, so the reason for that is the following. So what does a relativization proof use? It just uses two facts, right? Number one, that every Turing machine. Number two, that there exists a universal Turing machine, right?
yes, yes.
So suppose you could prove something for A and B using just these two facts. Okay. Now both these facts also hold true, even if you even if instead of looking at Turing machines, you look at Oracle Turing machines, right? So even
Right.
Oracle Turing machines have an encoding, and even Oracle Turing machines can be simulated using universal Turing machines, right?
So would you say like that whatever would hold for the complexity classes initially, it would also hold for with when they have oracle access. And for this the argument is that we can simply ignore the existence of that oracle. We won't use that.
Not exactly. Okay, so what will end up happening is suppose you have some step in your proof where you are arguing about the Turing machine MI. Now all you have to do is replace MI with MI to DO, and your proof will go through.
Okay.
So you are sort of right. You can ignore the existence of the oracle. Every step in your proof would still work in the presence of the oracle.
Okay.
Yeah,
Okay. Okay, that's right. Okay.
yeah. Okay, so if there are no other questions, we can end the meeting today.
Goodbye.
Bye.